Hey guys, I'm going to go over our Chapter 5 quiz. So question 1 says that probability of A is 0.25 and probability of B is 0.34. What is the probability of A union B if A and B are independent? And so that's kind of a key point here, that the two are independent. Because we know if they're independent, that means they don't share any outcomes. And so in order to find the probability of A or B, I can just simply add their two probabilities. So the probability of A union B when events are independent is just the probability of A plus the probability of B. So add those up, 0.25 plus 0.34, and the correct answer here is C. All right, question 2. An inspection procedure at a manufacturing plant involves picking 3 items at random and then accepting the whole lot if at least one of the 3 items are in perfect condition. If in reality 84% are in perfect condition, what is the probability that the lot will be accepted? So I'm doing the probability of at least one. And that's really hard to predict or to calculate because it could be 1 item, it could be 2 items, it could be 3 items. At least one, there's different possible outcomes. But at least one is the complement of none. So we can actually find the complement of the probability that none are perfect, and then that will tell us at least one. So first thing I want to see here, the probability that it is perfect is 0.84, which means that the probability that it is not perfect, so not perfect, is 0.16. Okay, so that's the probability that one lot is not perfect. I want to find the probability that all 3 lots are not perfect. So in order to do that, if I want the first one to not be perfect and the second one to not be perfect and the third one to not be perfect, that is the multiplication. That's where we multiply our probabilities. So I'm basically multiplying 0.16 times itself 3 times. So that's the same as 0.16 to the 3rd power. So again, because there's 3 items, that's what leads to the 3rd power. And so this is the probability that none are perfect. So to find the probability of at least one, I do 1 minus this probability. So 1 minus the 0.16 to the 3rd power, and we get the 0.996, so our answer is D. All right, 3, suppose that for a certain coastal city in any given year, the probability of a major hurricane hitting is 0.4, the probability of flooding is 0.3, the probability of both is 0.2. What is the probability of flooding given that a major hurricane hit? So I want the probability of flooding given hurricane. And this is equal to the probability of flooding and hurricane over the probability of just a hurricane. So this is where the formula comes in handy. I'm going to plug in what I know. So I know that the probability of the hurricane and flooding is 0.2. And I know that the probability of just a hurricane hitting is 0.4. So I will finish this, 0.2 divided by 0.4, and the answer is 0.5. All right, question 4. There are 2 games involving flipping a fair coin. In the first game, you win a prize if you can throw between 45 and 55% heads. And in the second game, you can win if you throw more than 60% heads. For each game, would you rather flip the coin 30 times or 300 times? So maybe when you first read this question, you were a little bit confused. So what are some ways and strategies that we could approach a problem that we feel unsure about? So one thing that I want to point out to you is think about the question itself, right? For each game, would you rather flip the coin 30 times or 300 times? What have we learned that relates to doing something 30 times versus doing something 300 times? What is the difference between only doing it 30 times versus doing it 300 times? And hopefully you're starting to think about the law of large numbers, right? We talked about how smaller sample sizes are not always as accurate as larger sample sizes. So the larger our sample size, or the larger the number of times that we do something, the better and better our results get. So now how could that relate to the problem itself? Well, we are flipping a fair coin, and we know that the odds of getting a heads or a tails is 50-50. So in the first game, I win if I throw between 45 and 55%. Well, this is pretty close to what we know is the theoretical probability of flipping a coin, right? We know theoretically you should get a heads 50% of the time. So using the law of large numbers, the larger my sample, the closer I get to the theoretical probability. So in game one, I would prefer to flip the coin 300 times. So in the second game, I win if I can throw more than 60%. Well, that is a lot higher than the theoretical probability. So ideally here, my best odds of winning is if I only do it 30 times, because we know that probability is unpredictable in the short term, right? So in 30 times, it's possible that I could get 60% or higher heads. So the answer here was D, 300 times for the first game and 30 times for the second. And I just want to make that theoretical probability is 50%, not the 45 to 55. All right, question 5. According to one poll, only 7% of the public say they trust Congress. In a simple random sample of 10 people, what is the probability at least one trusts Congress? All right, so 7% trusts Congress. That means that 0.07 trust and 0.93 don't. In order to find the probability of at least one, we use the complement of the probability that none trust Congress. So I'm going to use the 0.93. I have 10 people, so I need to raise 0.93 to the 10th power in order to get those 10 people all not trusting Congress. So that is the probability of none. And in order to actually get the probability of at least one, right, we want the complement of this. So I do 1 minus that. All right, so I'm going to plug this in real quick. I'm doing 1 minus 0.93 to the 10th power. And I get 0.516. So the answer here is D. All right, so our first typo here, I actually want the probability of B given A. I'm given the probability of A, the probability of B, and the probability of A given B. Now, I need to use this information to find what I want to find. I know, based on our formula, that the probability of A given B is equal to the probability of A and B over the probability of B. And I know the probability of the one that I'm trying to find is the probability of A and B over the probability of A. Now, I know the probability of A in order to find this one that I'm trying to look for, but I don't know the probability of A intersect B. So that's the problem. Right now, I can't use the formula because I don't know this one piece. But that piece is also in the formula for the one I do know. So I know the probability of A given B. I know the probability of B, and I can use those to solve for the probability of A intersect B. Then I'll plug that in and solve for the probability of B given A. So first step is to plug in probability of A given B is 0.2 equals, I'm just going to put X for our unknown, X over the probability of B is 0.4. I'm going to solve this for X, and I get 0.08. Now plug in for what we're actually trying to find. The probability of B given A is that 0.08 divided by the probability A is 0.25, so 0.08 divided by 0.25, and I get 0.32. All right, 7. A survey gathered information on the number of televisions in homes. If X is the number of televisions in a randomly selected home and we discard the uncommon situations of more than 5, then X has the following distribution. So I'm ignoring anybody that's more than 5. What is the probability that a home randomly chosen has at least 2 televisions? All right, at least 2 means that they could have 2, they could have 3, they could have 4, they could have 5. So the probability of having at least 2, when I have the probabilities for 2, for 3, for 4, and for 5, so I would just add up the probability of them having 2 plus the probability of 3 plus the probability of 4 plus the probability of 5. So 0.2 plus 0.11 plus 0.05 plus 0.03, and I get 0.39. All right, in question 8, is the following a valid probability model? The answer is no. There are 2 reasons why the answer is no. First off, if I add these probabilities, 0.2 plus 0.1, actually they do add to 1. Well, then that's not the reason. So the other reason that's right here as you look at it is that we have a negative probability, and that is not allowed. So just based on that alone, even though they add to 1, still, because there is a negative probability, that is not a valid model. We know that probability can never be negative. All right, number 9. Willy Wonka is selling chocolate bars with golden tickets. He claims that the odds of finding a golden ticket are 25%. You want to see if this is true. You buy 40 candy bars and find 5 golden tickets. Describe a simulation you could perform to test Willy Wonka's claim. A lot of you tried to apply the law of large numbers to this problem. And you said, go to the store and buy as many candy bars as you can afford. And you tried to simulate this using candy bars. But you cannot do that. In order to be a simulation, what we are trying to do is to simulate the claim, okay? We want to simulate a 25% chance. So me going to the store and buying lots and lots of candy bars is not going to simulate 25% because I don't know for sure that Willy Wonka is telling the truth. So what I have to do is simulate what he's claiming to be true so I can test the data we've collected. So we've already collected data that 40 candy bars out of 45 have golden tickets. I already collected this data. Now I want to simulate it and test my data against the simulation. So when you do a simulation, we came up with a few examples in our notes that you could do. You can roll a dice. You can use a deck of cards. You can use a spinner. You can use a random number generator. But the key is whatever you choose to do, it must simulate a 25% chance of winning. So some options that you could have used is to use a random number generator from 1 to 4. Say a 2 is a golden ticket. And you just record the number of 2s. And I would repeat this, right? I would take 40. Let me actually say this, right? So record number of 2s in a sample of 40 numbers. So that way I'm replicating buying 40 candy bars at the store, and repeat many times. Another option you could have done is a spinner with 4 options, because that would be a 1 in 4 or 25% chance. All right, number 10, draw and fill in a Venn diagram for the following. There are 78 students in Miss Frizzle's science class, and they named their favorite summer activities. 29 like sports. 43 like swimming. And there were 12 students who had selected both sports and swimming. So as I make my Venn diagram here, it's important to note that we have students who are in both categories. So the students that are in both, right now they're being counted twice because they answered that they like sports and they answered they like swimming. So when I first fill this in, I can put the people who like both in the middle. But I need the circle for sports. I need this whole circle to add up to 29. So right now there's already 12 in that circle. I'm going to do 29 minus 12. There are 17 students who chose just sports. Same thing for swimming, right? Here's my swimming circle. I need the circle itself to add to 43. So 43 minus 12, 31 students chose just swimming. Now, if you add these three numbers, 17 plus 12 plus 31, you only get 60. And we know that there's 78 students total in the class. Well, remember I said it's important that you include the box that represents your whole population. Because even though some students might not have chosen sports or swimming, they're still important to us. So I'm going to take the 78 students total in the class, subtract the 60 that are accounted for within our Venn diagram right now, and there are 18 students who fall outside of the favorite activities of sports or swim. All right, number 11 is our tree diagram. And so when I create a tree diagram, there's lots of reasons why you might choose to do one. And one reason is because you have multiple choices that have different scenarios within themselves. So if I wanted to find the probability of choosing a red marble, but I first have to choose a box, right? I have to choose a box and choose a red marble. it's not necessarily as simple as figuring out how many red marbles there are and then just taking that out of how many marbles total. Because the odds that I pick a red marble change depending on which box I pick. And it's more likely that I pick some boxes over the others because there's more of those boxes than there are the others. So because there's so much difference here that I want to account for, that's why a tree diagram is really helpful. So just getting started, it says there's 8 boxes, 3 contain 2 red and 2 green. The rest contain 3 red and 2 green. So what I would first do is break up my tree diagram based on the boxes. So I'm going to get started. We have maybe the A boxes that have 2 red and 2 green. And then I've got the B boxes with 3 red and 2 green. And now, what is the probability of choosing an A box or a B box? Well, there are 3 A boxes out of the 8 total. So the probability of going along the A box route is 3 out of 8. And then the B boxes is just everything that's left, so that leaves 5 out of the 8 total boxes. All right, now within each box, after I choose a box, there's different probabilities of either selecting a red marble or a green. So the A box, 2 things can happen. I could select a red marble or I could select a green. The probability of selecting a red in the A box is a 2 out of 4 or 1/2 probability. And the same with green. There's 2 green marbles out of 4. For the B boxes, same thing. I could choose a red marble out or I could choose a green. And what's the probability? Well, there's 3 reds out of 5 marbles total, or there's 2 greens out of 5 marbles total. Now, how do I find the final probabilities for each outcome though, right? This is the probability of an A box and red. So in order to find this one, I'm going to multiply 3/8 times 2/4. And I get 0.1875. And I do the same thing for all of these. So the same thing for the green, and I get 0.1875. Then for the B box, a B box and red, I'm going to do 5 out of 8 times 3 out of 5. And I get 0.375. And the last one, we got the 5 over 8 times 2 out of 5. And that is a 0.25. Now, if you remember right here, we have a check. If we've listed truly every possible outcome correctly, when I add these up, they should equal 1. And if you check these 4, they do. So we know that we've correctly calculated all of the outcomes. So this is a good tree diagram. Now, B says a player wins if they end up with a red marble. What is the probability of winning? Well, there's the possibility that you get a red marble along this branch. So the probability of getting a red marble is right here. Or you could get a B box and get a red marble, and that probability is right here. So to find the probability of winning with a red marble, I'm just going to add these two. 0.1875 plus 0.375. And I get 0.5625.